Hello students, in the present video, let us discuss about the different reactions of alcohols and phenols. Let us see the reactions. In the earlier video, I have explained reactions of alcohol that involves cleavage of oxygen-hydrogen bond. Now in this video, let us find few reactions that involves the cleavage of carbon-oxygen bond here for alcohol. And the number one reaction is reaction with hydrogen halide. When alcohol is reacted with hydrogen halide, we get alkyl halide as the product. Now here, the reactivity order of alkyl halide is from HCl towards the HI, the reactivity increases as because due to increasing size of the halogen, the bond dissociation enthalpy decreases in the order from HCl to HI. Now, for particularly HCl, since the bond dissociation enthalpy is very high, a Lewis acid catalyst, which is ZnCl2, is mainly used, and together the reagent is called Leucas reagent, the mixture of ZnCl2 and HCl. Here, ZnCl2 acts as a Lewis acid catalyst to break down the bond between hydrogen and chlorine to form the nucleophile Cl minus in this process. As we can see here, ZnCl2 with HCl, as because it accepts electron from chlorine, forming ZnCl3 minus, that breaks down to form ZnCl2 and Cl minus. This Cl minus acts as the nucleophile. So after protonation of the alcohol, when Cl minus combines with this alkyl group, the carbon oxygen bond is broken. That means water, H2O gets removed from the alcohol, so that we can get the alkyl halide, here alkyl chloride. Now the order of reactivity of alcohols, as you know that towards the 3-degree alcohol, the reactivity increases. So this particular reagent, Leucas reagent, is also used for to distinguish between 1 degree, 2 degree, and 3 degree alcohol. We can take example here, say ethanol as primary alcohol, isopropyl alcohol as the secondary one, and tertiary butyl alcohol. If we use ZnCl2 and HCl, since 1 degree alcohol is least reactive, therefore with Leucas reagent, the formed alkyl halide, the alkyl halide is formed very slowly. This ethyl chloride is formed very slowly, and the medium in which is aqueous medium, in the aqueous medium, this alkyl halide is insoluble. Therefore, a turbidity is formed, but it takes very long time. For 2-degree alcohol, it is found that between 5 to 10 minutes, the turbidity is formed due to formation of the alkyl chloride. Here from isopropyl alcohol to isopropyl chloride gives rise the turbidity in little faster time than 1 degree alcohol. And for tertiary alcohol, the turbidity is formed instantly, as because tertiary alcohol is most reactive among 1 degree, 2 degree, and 3 degree alcohol. So therefore, from the ease of turbidity formed, we can predict that which one is 3 degree alcohol, which one is 2 degree, and which one is 1 degree alcohol when treated with Leucas reagent. Next, let us find dehydration of alcohol. Dehydration of alcohol is carried out in presence of concentrated sulfuric acid at higher temperature, 170 degrees Celsius, where we can find that the product comes as alkene. And here, if we take this example, butanol, there is 2 beta carbons that can be removed along with this OH group from the alpha carbon, resulting 2 different alkenes. We can find that this more substituted alkene butene will be the major product, that is also called SEDJ product, and this can be understood from the mechanism of this dehydration of alcohol. Let us find as an example, propan 2-ol is taken, treated with concentrated sulfuric acid, giving rise this propene. This reaction actually follows formation of carb-cation intermediate. So in case of butane 2-ol, the product that is forming, giving rise the major product, actually initially the alcohol OH group will be removed, their carb-cation will be formed, but due to more stability of this but 2 in than the but 1 in, it will be the major product. It is more stable due to presence of more number of hyperconjugable hydrogen atoms. And here, if we follow the mechanism, it follows the three-step process. The dehydration of alcohol. Number one is protonation of alcohol from the acid. The H plus formed uh, gets combined with this alcoholic group, OH group, to form this intermediate. Then in the next step, water gets removed. That is called deep hydration to give rise this carb cation. So, and after that, from this carb cation, hydrogen is eliminated. That means the anion coming from the acid is taking away the hydrogen from the beta carbon, resulting this alkene. So this is the deprotonation step. And since initially acid was initiating the reaction, and at the end the acid is returned, so we can say that it is an acid catalyzed reaction. So these three steps are involved in acid catalyzed dehydration reaction. And the reactivity order in this reaction also increases from 1 degree towards the 3 degree alcohol. We can follow this thing from the reagent used for this reaction, dehydration. We can see that for 1 degree alcohol, concentrated sulfuric acid with higher temperature, 170 degrees Celsius is required. If we use 2 degree alcohol, for that we can use 85% phosphoric acid, which is mild, I mean less concentrated than the, or less reactive than the concentrated sulfuric acid. So using phosphoric acid we can get the elimination product. And for 3 degree alcohol, 20% phosphoric acid can sufficiently give rise the alkene. So depending on the reagent, we can follow that in this dehydration of alcohol towards the 3 degree alcohol, the reactivity increases. Here it is, the 2 degree alcohol, this one, and this is tertiary butyl alcohol, the 3 degree one. Now let us find the next reaction, reaction with phosphorus halide. This reaction we can find also in haloalkane haloarine chapter, where alcohol, when reacted with phosphorus halides, it gives rise the halogen substituted product. By using phosphorus pentachloride or phosphorus trichloride, we can get this products. See here, when phosphorus trichloride is used, the byproduct is phosphorus acid, and when phosphorus pentachloride is used, the byproducts are different. Phosphorus oxychloride and HCl are formed in by if other halide is required to bring replacing OH group from alcohol, we can use red phosphorus with bromine as well as iodine, giving rise this halogen substituted product. So alcohol can give this kind of product also. Here we can follow the breaking down of carbon oxygen bond is also taking place. Next is oxidation of alcohol. When alcohol is oxidized, uh, particularly primary alcohol, then it first gives rise the aldehyde and then to carboxylic acid. If we use stronger oxidizing agent like dichromate in presence of acid, or acidified KMnO4 or alkaline KMnO4 followed by acidification. These are strong oxidizing agent that oxidizes alcohol uh, up to carboxylic acid. But if we use mild oxidizing agent, that is chromium oxide or PCC, we can get aldehyde. The end product may be aldehyde from 1 degree alcohol, and from 2 degree alcohol we can get ketone. Now, if ketone is oxidized, I mean 2 degree alcohol is oxidized by using strong oxidizing agent, then after formation of ketone, there is possibility of breaking down of this ketone to form further fragmented carboxylic acids by following Popov's rule that we can learn in a different video. And here you can follow that when this mild oxidizing agent is used at the side chain, if there is any unsaturation, it is not being disturbed. So this reagent, weak oxidizing agent, are suitable for synthesis of organic compounds. So PCC is very useful, which is pyridinium chlorochromate. This is the structure drawn here. You can see. So the oxidation of 1 degree and 2 degree alcohol to aldehyde and ketone is possible by using weak oxidizing agents. Now, this thing can also be achieved by dehydrogenation of 1 degree and 2 degree alcohol when they are heated with metallic copper or silver at around 300 degrees Celsius. Primary alcohol gives by dehydrogenation the aldehyde. Secondary alcohol gives ketone. But for tertiary alcohol in this process, instead of dehydration takes place that results formation of alkene. So these were few reactions of alcohol where carbon oxygen bonds are broken. Now let us find the reactions of phenol. When phenol is heated with metallic zinc, then the zinc removes the oxygen, resulting benzene. So zinc dust with phenol, when heated, benzene is formed. Then oxidation of phenol when in presence of air or chromic acid, or dichromate in presence of acid, when phenol is treated with these reagents, it gives rise dark colored, brown colored uh, parabenzoquinone. So therefore, when phenols, I mean bottle of phenol is kept open in lab, we can find that it turns to brownish due to formation of this parabenzoquinone. Then very important name reaction is that Kolbe's reaction, when phenol is first treated with aqueous alkali to form this phenoxide ion, and when it is next treated with carbon dioxide and followed by acidification, it gives rise salicylic acid, that is carboxylic acid group is coming at the ortho position of this phenolic group. We can follow that from the alkoxide. In this way, the attack of the ring towards the electrophilic center of carbon dioxide takes place, and that follows the acidification to gives rise the salicylic acid. Then next, another important reaction is Reimer-Tiemann reaction. Reimer-Tiemann reaction is carried out with chloroform in presence of alkali. That is, when phenol is treated with chloroform and alkali, then first of all, this orthoposition, at the ortho position, this CHCl2 group is coming. When aqueous alkali is present, that is present in the medium, displaces, substitutes this halogen, giving rise this intermediate. But at the carbon holding 2 OH group is unstable. Therefrom, when in the reaction medium, uh, water is getting removed to give rise this intermediate, that is the aldehyde group is coming at the position, ortho position, following acidification gives rise the salicylic acid. That means when phenol is treated with chloroform and alkali and followed by acidification, salicylaldehyde is formed, which is named as 2-hydroxybenzaldehyde. Next, electrophilic substitution reaction. Now, phenol OH group is an group that donates electron into the ring. It is electron donating group. Therefore, in presence of phenol, the ortho and para position gets activated towards electrophile, and therefore, on nitration of phenol, when dilute nitric acid is used, it gives rise ortho and para nitrophenol. Among that, para product is major one due to less steric effect. We can follow that. Here we don't have to use concentrate sulfuric acid and concentrate nitric acid for this electrophilic substitution reaction, that means for the formation of NO2, as because phenol is so reactive, it activates the ring, and in presence of dilute acid, nitration is possible. And if concentrate sulfuric acid, nitric acid is taken, then all the ortho and para position gets substituted with nitro group, giving rise to 4,6 trinitrophenol, known as picric acid. Now, next is bromination. If bromination is carried out in a nonpolar solvent, then uh, ortho and para bromo phenol is formed. Here we can follow that in presence of phenol, polarization of Beer2, that means this kind of polarization, that means this is the electrophilic center formed in presence of phenol, and that means we don't require any Lewis acid catalyst for this reaction, giving rise this ortho and para substituted product. And if the polar solvent is used, all the ortho and para position gets uh, substituted with bromine, giving rise a white precipitate of 2,4,6 tribromophenol. This reaction, that means treatment of phenol with bromine water, giving rise this white precipitate of 2,4,6 tribromophenol, can be used for the identification of phenol in uh, practical chemistry. And the last reaction is also used for the identification of phenol by treatment with neutral ferric chloride, that gives rise a violet complex like this. You can follow that. Here Fe3 plus is there in the complex. The phenoxide, 6 moles of the phenoxide ion is involved. This is the violet color complex, and from this violet color complex formation, we can identify phenol. This reaction is used for the identification of phenol in the practical chemistry. So these are the few reactions of phenols. Thank you.